Today, we're going to start by modeling drug levels in your body. And we're going to start with a one-time dosage. So you're taking one pill. Talk about how to model that. And then we'll move on to modeling taking one pill over and over again at a consistent amount of time between dosages. It could be 4 hours, could be 6 hours, 8 hours, 12 hours, 24. It could be anything. With an idea that we want to stay below an upper limit that could be dangerous for the amount of the drug in our bodies. That's what we'll focus on. We could also focus on staying above a lower limit to make sure the drug is effective if it needs to be continuously effective. And modeling this with differential equations ultimately will also allow us to generalize it to include not only individual discrete drug dosages, but like an intravenous admission of drugs into your body, where it's coming in one drip at a time, effectively every second of every day, even though it might not be dripping once per second. So this is a one-time dosage to start with. We are going to use a lot of letters today. A lot of letters some representing variables and some representing constants. But those constants are what I also call parameters that we want to allow ourselves to think about what could happen if they are different, like with a different drug, for example. So a lot of letters to keep track of. We're going to let D be the dosage amount. And just to be specific, let's go ahead and pick specific units, say in milligrams. With drugs, one way to measure how long the drug stays in your bloodstream is to measure the half-life of the drug. Drugs do decay, you can verify by experiment, according to exponential decay. And if you know about exponential decay, whether it's radioactive decay or something else, there's something called a half-life. We could let H, for example, be the half-life. It's an amount of time, and probably the most typical unit to use here would be in hours, since you're usually taking a drug once every certain number of hours. We're going to let Q be the quantity or amount of the drug in your bloodstream. And it's a variable. It's really a function of time at time t in hours. D and H are constants or parameters, if you prefer. Q and T are true variables for the differential equation, and ultimately the solution, the function, the exponential decay function that solves the differential equation. But we do want to write down a differential equation to model this. Not that you have to do it that way. You could just say, I'm going to use an exponential decay function right away. But we are learning about differential equations, so that's one reason to use a differential equation. A more important reason to use a differential equation is it does give us flexibility to deal with more complicated situations like the intravenous administering of the drug. What is our law for how the amount of the drug varies? The rate of change of the drug, dq dt, you can measure is proportional to the amount of drug that's present. I'll use the proportionality symbol. It's proportional to the amount of drug that's present. In other words, at the most intuitive level, the more drug that's in your body at any given moment in time, the faster it's decaying. Now, how is it decaying? Well, it could be through various measures. It could be through urination. It could be through sweat. Most likely, the drug is decaying because it's being used, right? The molecule is binding to other molecules in your cells or something, and so it's being used. Its chemical reactions are going on. And so while the molecules may still be in your body, the atoms they're changing. And so the drug itself is not in your body at as high an amount or concentration. That's our law. And we can convert this law to a differential equation as long as we have a constant of proportionality. So this being proportional to means really there's a constant of proportionality. So dq dt is that constant times q itself. Because it's decay, dq dt has got to be negative. The slope of your q function as a function of time is going to be negative. So since q is positive, I need a negative constant of proportionality. Let's emphasize that by using a negative sign. Negative k times q for some constant negative q. That entire thing is your constant of proportionality. Not just the k, but the negative k. Constant of proportionality. It's negative. K is positive, so that negative q is negative, is worth keeping track of in your mind and symbolically. Again, it's not that we have to write a negative sign. We could just write a k times q and say, hey, k is negative. Or solve for it and see that k is negative. But we think it's going to be negative, so why not call it negative q to emphasize that? K is positive, so negative k is negative. Now, we can certainly solve this differential equation by separation of variables. K is a constant. Q and T are the variables. To separate variables means to say get the Q's on the left side and the T's on the right side. So I divide both sides by Q and quote unquote multiply both sides by dt. I get dq over q equals negative k dt. And then I could integrate and solve for q. This is a simple enough equation, though, that you can just guess. Q is going to be an exponential function of t. I'm going to do something new today, and I'm going to do this new thing from here on out every day for the rest of the semester, probably. The book doesn't do this, what I'm about to do. But I think it's worthwhile to do, to give this function another name. Don't call it q equals q of t, because that's abusing notation. But give the function a name. I'm going to use the Greek letter phi, or phi if you prefer. Phi is going to be the function name of the solution. I'm not calling it f here because I'm going to reserve the letter f for the right-hand side of the differential equation, like I did last week already when we talked about slope fields and Euler's method. I used f for the right-hand side. I want to reserve f for the right-hand side. This is somewhat traditional, though again, our textbook does not do this. I use this kind of notation a lot in differential equations with linear algebra. I'm not sure if Dr. Auk uses it in the plain old differential equations course. I probably should ask him if he does or not. It is a function of time t. And you already know what the answer is. You know this. It's q naught, q sub 0, the initial amount, times e to the negative kt. Where q sub 0, the q naught, that's got to be the same as the dosage, or at least it would be if we assume, for simplicity's sake, that when you take that pill, it's in your bloodstream instantaneously. Of course, that's not true. You got to swallow it. Your stomach has to digest it. It's got to get into your small intestine before it gets into your bloodstream. But if that's a fairly quick process, maybe only taking a minute or two, which it might be for some drugs, not the slow release ones, but some drugs it might be, they probably dissolve pretty quickly, get into your bloodstream pretty quickly. It's a good enough approximation. It's a nice simplifying assumption, which is part of what mathematical modeling is about, is deciding what things to ignore, in this case, swallowing and digesting, for the sake of simplicity and approximations that are good enough. So with that assumption, I'm going to replace Q naught with D, the dosage amount. This is assuming Assume drug is in your bloodstream instantaneously. So this is exponential decay. The graph would look like this. This would be Q naught equals D right there. But wait a minute, am I forgetting something? I am forgetting something that I wrote down on purpose. But I'm forgetting the half-life. What's the half-life? The half-life is the amount of time, T, so that you end up with half the amount you started with. 1/2 D right there is going to occur at time capital or time H for half-life. And it turns out this takes either experimental evidence if you are confirming an exponential model, or mathematical evidence if you know the exponential model works, that the half-life doesn't depend on Q naught. In this case, it doesn't depend on D. It doesn't depend on how many milligrams you take, that this half-life is the same. Why does that happen mathematically speaking? We can solve for H by setting 1/2 D equal to D e to the negative K times H. That equation defines the half-life. The half-life is an amount of time where the function, when you plug it in for T, equals half the amount you started with. That's what half-life is. And then we can do algebra to solve for it, and the D's cancel. The D doesn't matter. So mathematically speaking, that's why the D doesn't matter. Solve for H, take the log of both sides. ln of 1/2 will be ln of this, and the E and the ln cancel, leaving you with negative KH. Solve for the half-life. One way to write the half-life is as ln of 1/2 divided by negative K. That might look like a negative number, but it's actually not, because ln of 1/2 is a negative number. Yes, negative K is negative, but negative divided by negative is positive. A more typical way this is written is to use a property of logarithms to say that's ln of 1 minus ln of 2, right? Ln of a quotient is the difference of the logs. But ln of 1 is 0. So that becomes negative natural log of 2. So this becomes negative natural log of 2 divided by negative K. And then the negative signs cancel. So you're left with ln of 2 divided by K as a more typical way to write the half-life. And then you could use that to figure out, well, if you know K, you can figure out the half-life. We were kind of pretending the other way around. We were pretending we know H, so we want to figure out K. But this equation, H equals ln of 2 divided by K, is really pretty symmetric in H and K. If I solve it for K, the roles of H and K just get swapped. K is going to be ln of 2 divided by H. So as an example, if the half-life happens to be 4 hours, what is K? Ln of 2 divided by ln of 4, or excuse me, ln of 2 divided by 4 will be what K is if the half-life is 4 hours, about 0.1733. H equals 4 would imply K is about 0.1733, which means the constant of proportionality itself, negative K, is about negative 0.1733. And you can use this information to figure out, how long is it going to take for the amount of the drug to go down to, say, 1% of what you started with. Maybe we should do that. Let's say we want to figure out how long until it's 1% of the starting amount, the dosage. Maybe even at 1% of the dosage, it's still effective. I mean, that's probably not likely, but maybe. 1% of the dosage is 0.01 times D. That's 1% of D. Set that equal to D e to the negative K times T. Okay, let's go ahead and get it in terms of K first. And we'll also write it in terms of the half-life H. Solve that equation for T. Once again, the D's cancel. The dosage doesn't matter. So you're left with 0.01 or 1/100th equals e to the negative KT. Take the log of both sides. Divide both sides by negative K. T is going to be ln of 1/100 divided by negative K. Once again, we can use a property of logarithms to say that this is ln of 1 minus ln of 100. And that's a 0. So this becomes negative ln of 100 over K, negative K, excuse me. And then the negative signs cancel, and T will be ln of 100 divided by K. So for example, if the half-life is 4 hours, so that K is 0.1733, the amount of time it takes to go down to 1% of what you started with will be ln of 100 divided by K. Whoops. Ln of 100 divided by K, about 26.6 hours. Does that make sense? You can think in terms of powers of 0.5 to figure out if it makes sense. Powers of 0.5 referring to half-life. Half-life is 4-hour increments. To get to 26.6 hours, that's like a little over 6.5 increments of time. 6.5 half-lives. So if I raise this to the approximately 6.5 power, it should be close to 0.01. Yeah, not too far away. Alternatively, if I keep multiplying 0.5 times itself 2, 3, 4, 5, 6 times, and then to 7 times, I'm under 1%. So that's how you model a one-time dosage. Okay, now we want to get more sophisticated and model many dosages. Still the same dosage amount each time, D, because you got the same pill each time. But ultimately, the question is, how often should you take these pills? This is nice to think about graphically first. I'm going to make a big graph here. And the book actually does this in the reading from like about a month ago, near the beginning of chapter 9, when you first learned about geometric series. They were talking about drug dosages in the reading. And I'm going to do pretty much the same thing that they did. Try to model it graphically first, and then we're actually going to use geometric series to try to figure out how often should we take the drug of dosage D to guarantee we don't get above some dangerous level. What happens with the first dose, say at time T equals 0, you go from having 0 drug in your body to having a certain amount. In fact, that certain amount has got to be Q naught or D. And actually, I'm going to call it Q1 actually in this case, because it is going to be the amount in your body right after the first dose. I mean, I could call it Q0 and call it the initial amount as well. But this notation is a little bit more consistent with chapter 9. What happens? It goes in your body. It's effectively instantaneously into your bloodstream all over your body, or at least in a short enough time period to ignore. And then it decays because your body's using it. Maybe it gets excreted. It's decaying exponentially. It's got a certain half-life. I could mark the half-life on here, but I don't want to. I'd like to just let it go until it's some certain time. I'll call that time capital T. Capital T is going to be the time between dosages. Capital T is time between doses. Is it doses or dosages? I'm not sure. In hours. Probably bigger than the half-life. Maybe it gets down to, I don't know, 20% of what you started with, and maybe that's still effective in addressing whatever issue you need it to address. Then at time capital T, we take another dose. The dose is still an amount D. So the jump here is going to be still by amount D to another new amount. What would that amount be? This starts to get a little tricky. I guess I better add D to whatever the second coordinate of that point right there is. The amount at time capital T. What is that amount? That's got to be D e to the negative K times capital T. Right? Because at time 0, D was the Q naught. It's decaying until time capital T. I'm multiplying it by e to the negative K times capital T. So this new amount right here has got to be D plus that. D plus D e to the negative KT. And then that new higher amount, I could call it Q1 or Q2. That decays another T units of time to time 2 times capital T. What does it decay to? What's the second coordinate of the point that's going to be missing there right before the jump discontinuity? Think about it here. This new amount, the second coordinate of that point, D plus D e to the negative KT, that's got to decay for an amount of time capital T. It's got to get multiplied by e to the negative K times capital T. And then I could distribute that through the parentheses and write it as D e to the negative KT plus, think carefully here, D, when you multiply those two things, the exponents get added, right? Negative KT plus negative KT becomes negative 2 KT. And then to find this point right here, right there, I've got to add D to that. That's the dosage amount. So the second coordinate of that point is D plus that. D plus D e to the negative KT plus D e to the negative 2 KT. Is this feeling familiar at all? That kind of sum, that should look a little familiar. That is a geometric sum, a finite geometric series. That's going to be Q2, or Q3 actually. That's Q3. Getting these subscripts mixed up. In general, Qn, the amount in the bloodstream just after the nth dose, which will, if you look at the pattern here, like the third dose is at time 2t. The fourth dose would be at time 3t. This is at time n minus 1 times t. Follow the pattern. It's going to be D plus D e to the negative KT plus D e to the negative 2 KT plus dot, dot, dot. The last one's going to be what? This one, the third dose, the coefficient of K was negative 2. So here at the nth dose, the coefficient has got to be the negative this. This is going to be D e to the negative n minus 1 KT. A finite geometric series it equals, you don't have to even worry about convergence because it's finite. It equals the first term, D, the leading term, times 1 minus, what's the common ratio? Yeah, e to the negative kt. That's got to get raised to a power equal to the number of terms divided by 1 minus the common ratio. That is how much of the drug is in your body right after the nth dose. And K, by the way, again, is natural log of 2 divided by the half-life. You could write this in terms of the half-life H if you prefer. N is the number of the nth dose. D is the dosage amount. Now remember, what are we ultimately interested in here? We're interested in knowing, do we stay below some upper limit U? That's where the drug gets toxic in your body. We'd like to for sure stay below U. Maybe we even want to stay below, I don't know, U minus 1 or something, or U minus 2 to play it safe. But for sake of simplicity, let's just assume we stay below U. How can we figure out if this ever goes above U? What conditions will guarantee it stays below U no matter how big N is? Why don't we let N go to infinity? What's going to happen as N goes to infinity here? This thing goes to 0 as N goes to infinity. Why? Because e to the negative kt is e to a negative power is less than 1. And also not negative. It's between 0 and 1. I keep raising it to higher and higher powers. It's going to go to 0. The whole thing approaches d times 1 minus 0, which is just d, over 1 minus e to the negative kt. Hey, yeah, that looks like a over 1 minus r from geometric series. I didn't actually have to do all this derivation, but I did anyway. I can think about infinite geometric series to help me guarantee that I stay below U. But again, how do I guarantee that I stay below U? I could say, set this to be less than U, and I could solve it. For the sake of simplicity, set it equal to U and solve. And that'll give you the smallest that capital T should be. I'm after the value of capital T, by the way. U is the upper limit above which it's toxic. That's a fixed number. D is the dosage amount. That's a fixed number. K is natural log of 2 over the half-life. That's a fixed number. It depends on what the drug is. It's T that I want to know. So solve this for T. It looks kind of hard at first, but if you do a little rearranging, divide both sides by capital U and multiply both sides by 1 minus e to the negative kt, then it looks a little easier. A little more rearranging reveals e to the negative k capital T is 1 minus d over u, which if you like, you can write as u minus d all over u. Trying to solve for capital T, so I take a log of both sides to get rid of the e. I could use a property of logs here. I've got the log of a quotient. That would be the difference of the logs. Do I have to do that? No. I could now just divide both sides by negative k. I could write T as negative 1 over k ln of u minus d over u. And that would be an equation that gives the smallest that capital T should be to guarantee you don't get above toxic levels. In reality, you don't want to get close to toxic levels, so probably you should make the actual dosage interval a bit bigger, so it has more time to decay. That's very powerful. This is giving me the answer no matter what K, D, and U are. Of course, it's going to have more meaning if you pick some values. If I go back to my previous example where the half-life was 4, so that again, K is ln of 2 divided by 4 is 0.1733. And just pick U to be, I don't know, 30 milligrams and D to be 5 milligrams. If D is 5 and U is 30, let's go ahead and write those down. So I'm assuming the half-life is 4. That implies K is about 0.1733. If I make the assumption that U is 30 and D is 5, then I get T is negative 1 over 0.1733 ln of 25 over 30. And what does that turn out to be? Ln of 25 over 30 is a negative number. I divide that by negative 0.1733. I get a positive number. For sure, wait at least an hour. An hour and a few minutes. Okay, for sure, wait at least that long. Obviously, in general, you'd want to wait longer. Of course, if you use different numbers, you'll get a different answer. If, for example, the dosage is even bigger, maybe 10 instead of 30, you do ln of 20 over 30, ln of 2/3, and divide that by negative 0.1733. And that's saying to wait at least 2 1/3 hours. Maybe wait 3 or 4 hours to play it safe. In reality, you also want to think about not just an upper safe limit, but a lower effective limit. And you'd want the difference between them, U minus L, to be at least D, maybe bigger. That you would want to think about as well, so that you don't wait too long between dosages. Okay. So all this, both the differential equations and the series, are applications of recent stuff to medicine.